Women's fault. They keep like their chests in front of the screen and taking away from the memes.
Okay, we're gonna go over number 7. I'm gonna go over like number 7, 8, maybe one more. So you'll notice these are they're all, well, the first few are polynomials, and it's like it's not very exciting, right? I mean, we've been graphing polynomials for a while, but the point of these questions is just to get us to look at how can you go from a function to a graph of the function while thinking about things like concavity and derivatives and stuff. So anyway, I tried to give you a little guideline here, A, B, C, D, E, F. So for number 7, here's your function. Okay. So it says to draw f prime and f double prime number lines. So that requires us to take the derivative first. The derivative is 4x minus 12, and then take the second derivative, which would just be 4. Okay. So you've got your, I guess in this case, it's actually a y prime number line. It's not really an s prime number line, but you get the idea. The first derivative number line and a second derivative number line. So what's the critical value? What would make this either 0 or undefined? 3. Just 3. It's the only thing. Okay. So keep in mind, if this is a equation that, like, say, generated, say, asymptotes or something, you'd have to consider that on your number line. So anywhere where the derivative is 0 or undefined goes on here, and then we just go pick any number less than 3, 2, 1, whatever, plug it in. Is y prime negative or is it positive? Negative. Now, obviously, nothing groundbreaking here, right? It's a parabola, so it's going to go decrease, increase. Right? So that should feel good though, because you're like, okay, everything is making sense, nothing surprising. Then, well, this guy's always positive, so this guy just gets a plus sign. There's no critical values, so no inflection points. Again, that should be like, sweet. Okay, that agrees with my intuition about a parabola, and so we're going to sketch a little graph of it. Now let's get the local extrema. So what's the x value that the local extrema will happen at? 3. Okay. This next part it's not the most critical thing, but it it sometimes is useful where you say, what actually is this point here? 3 what? 0. Okay. By the way, this drawing's not going to be to scale, just full disclosure here. What's that y value? What's the y-intercept of the function? 11. And then, so how could I get this point? Kind of the same way I got that point, which is just to plug the x value into the function. So if I plug 3 in, I get 9 times 2 minus 12 times 3 plus 11. So what is that? 29. So -7. Is that right? Are we all okay with that? How we got that number? No? Yes? Possibly? Okay, so all I'm pointing out is, in general, anytime you want, you can plug in some x value, some relevant x value, and get the y value out of the function, okay, if you need to. All right, did we get everything? So, yeah, I mean, there we go. So you can label this number line too. This tells us that we're decreasing, increasing, and then this is concave up. So then does the picture make sense for everyone? No one finds the connection between this, and this confusing? Okay, sweet. Let's do one that's a bit more challenging. number 8. Cubic this time. Before we do any actual calculation, do you guys understand how if I just drew some random cubic off the top of my head, how this would go? Think of the derivatives. The function goes increasing, decreasing, increasing, so the derivatives must go positive, negative, positive. And how about concavity? Concave down, inflection point, concave up. Make sense? Okay. So that's what we're kind of expecting out of this. Unless they throw us a curveball and it does some weird thing like where it never actually decreases, that's the only thing that maybe we're keeping an eye out for on a question like this. So, not for a cubic, because calculus is actually a great class to start addressing things like how come a cubic can't do this? What's stopping it? And one of the reasons for that is imagine taking a cubic. So look at this thing. How many spots does this thing have like a derivative equal to 0? Quite a few, right? Well, can a third degree, so write some random third degree polynomial. X cubed minus 7x squared plus 6x plus 2. And take the first derivative of that, and you get a quadratic. So how many places can a quadratic equal 0? Only 2. So what calculus tells us is that a cubic can have at most 2 Humpty Dumptys. It can't have more than 2 Humpty Dumptys. But then that raises further questions. Well, how do you know that this thing can only have 2 zeros? Which you could answer that graphically. Like I know the shape of it. A parabola can only hit 0 2 times. Or you can get into something called the fundamental theorem of algebra, which gets into like how an nth degree polynomial can have at most n real roots. So anyway, good question. Good food for thought. So, and you could have repeated the same argument for concavity. Like a cubic can only have, it could have a concave up and a concave down, but it can't have more than that because its second derivative can't change from positive to negative more than once. Okay, f of x equal, that's not a 3. That's not the number I wanted to write. That was more like a 6. Okay. First thing I should do is what? Take derivative at 6x squared minus 6x minus 12. I'm going to leave myself a little bit of room here because I've got to answer the question, when does this thing equal 0, right? Which is kind of a whole algebra problem in and of itself. So let's take the second derivative while we're here. Second derivative would be 12x minus 6. We all okay with that? Okay. So, all right. So we got to answer the question now. When does this thing equal 0? So as I'm setting up that question, I'm going to kind of do 2 things at once. I'm going to factor out that 6 as I'm setting it equal to 0, just to save myself a little bit of energy. All right, so solve this. What do I get? Minus 2. That seems right. And so the critical numbers that go on my number line, my f prime number line, are -1 and positive. And then I already kind of know what these are, right? Because I already kind of have in the back of my head the shape of a cubic. And so I kind of already know it's going to go plus, minus, plus. But just to test out, plug in -3, and you have positive times negative, which is positive. Does that make sense, what I was doing there? You can plug it in here if you want, but I think it's much easier just to plug it into the factored form. Plug in, let's say 0 seems good. Positive times negative times positive makes a negative. And then if I did the same thing by plugging in, say, like 5, positive times positive times positive makes a positive. So that tells me that my function goes increasing, decreasing, increasing. Cool beans? All right, this guy, what is the x value that makes this be 0? 1/2. Right? If I plug in a number bigger than 1/2, like say 7 million, I'd have a huge number -6, which is a positive. But if I plug in a number smaller than 1/2, say 0, I get a negative value. So what does this tell me? This tells me that my function is concave down and then concave up, which, again, hopefully that agrees with, oh yeah, my mental image of a cubic function agrees with that. So that's good. Time to graph it. Here's -1. We're not gonna, so like I said before, we're not going to be like super concerned with y values. It's not really our focus, but try to get sort of tethered to something like, what's the y-intercept of this function? 5. If I plugged in zeros, 5. So just keep that in mind. So what's happening at -1? What kind of thing is happening? At -1, it's changing from increasing to decreasing. So what's the name for that? Extreme. Yep.
Yeah.
Local max. Right? So if we're increasing and decreasing, there's going to be a local max there. So there's going to be a local max at -1. And what happens at 2? Local min. So there's going to be a local max when x is -1, and a local min when x is 2. And then what happens at 1/2? What's that called? When it changes
Point of
from.
inflection.
Very good. Point of inflection. So an inflection point, or point of inflection, is going to occur when x is 1/2. And so here's where, yeah, if you're really fastidious, I guess you might plug into and say, what is my, like, am I actually going to be below the x-axis or above? But like I said before, we're not like super concerned with that, so it's okay if you just eyeball it. So I don't know, it could be, for all we know, it could be something like this. Try my best to put my inflection point. You see what I'm talking about here? Local max at -1. Local min at 2. And then there's my inflection point at 1/2. Cool beans? So concave down, concave up. And then for this, increasing, decreasing, increasing. So it all fits together. Yeah. I think this might actually be below the x-axis, but anyway, like I said, it's just, we're mostly just concerned with getting those critical values and stuff. So, what are we at? Okay, we're out of time. Sweet. So there you go. That should be a good model for you to finish the rest. Tomorrow we'll have some work time. Yeah. So that covers pretty much everything you got to know.